Example 2.14 is going to show us how to use the intermediate value theorem to guarantee the existence of a root, or a zero, of a polynomial. So let's remind ourselves of what the intermediate value theorem stated. If we have a point in our domain A and a function value there, f at A, and we have another point B and a function value there, f of B, and this function connects f of A and f of B continuously. Right, you can draw that without picking up your pencil. Then for any y value between f of A and f of B, there's going to exist some c value, some point in the domain that gives you that y value. So for instance, here, I could take this y value right there. That's in between f of A and f of B. And because I connected f of A and f of B continuously, there's going to be at least some c value. Right? There could be several c values, but there's going to be some point in my domain that hits that y value underneath the function. Another way of saying this is that if you can connect to this point continuously, then you have to hit all of the points in between them. Now, a corollary to the intermediate value theorem is showing that zeros can exist. So let's imagine that here's my x-axis, and I've got A right there in my domain, and B right there in my domain, and I've got a function that's continuous over this interval. If I can show that f of A is negative, so it's below the x-axis, and I can show that f of B is positive, meaning it's above the x-axis, then the only way for this function to continuously connect f of A and f of B is to pass over the x-axis or give yourself a zero. All right, now putting this all together, let's work on this example 2.14. I want to show that this cubic polynomial, x cubed minus x minus 1, has a root, or a zero, somewhere between 1 and 2. So first, if I'm going to use the intermediate value theorem, I need this function f of x to be continuous. And this is very clearly continuous. It's a third-degree polynomial. It's going to exist everywhere, and it's going to be continuous everywhere. The limit everywhere will return the same value as our function. So f is continuous on this interval 1 to 2. So that was needed for the intermediate value theorem. And now let's look at f at the left endpoint at 1. F of 1 is going to be 1 cubed minus 1 minus 1 for a value of minus 1. So far, here's 1, and our function has a value of minus 1 there. Now let's look at the function at 2. This would be 2 cubed minus 2 minus 1, or 5. So over here at 2, we have a y value of 5. Now, because this function is continuous over that interval, we're going to continuously draw a line from this point to that point. And I'm guessing on what that line might look like. But you can see that there's definitely a zero inside the interval. Because I showed that at 1, the function was below the x-axis. At 2, it was above the x-axis. So at some point, and I don't know the point, but at some point between 1 and 2, the function has to cross the x-axis and give yourself a root. So by the intermediate value theorem, there exists a c inside the interval 1 to 2, such that this function at that point gives me a zero, right? This here is that c value.